Section 2.3 is on page 12, talks about graphs and graphs that enlighten and graphs that deceive. We start off with a dot plot. Dot plots graph each dot value as a dot above a horizontal scale given right there. Dots represent equal values that are stacked. So for example, draw a dot plot of the following amount of cash that 13 people have in their wallets. One person holds a 25, so if this is 20, this is 40, this is the mid, that's 30. So those are 5 each. 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150. There. So each of those marks is a 5. 25 would be right there. 30 would be right there. 35 would be right there. 35, you would go above it, stack it. Another 35. 3 40s. 2 45s. 150. 160. And 150. There. This is a dot plot. Horizontal line would be the dollars, and you just stack those on top of each other. What is the shape of the distribution? Well, if you really look at it, that's one main reason for looking at this. If you try to graph a curve around it, it looks like, at least this much, it looks like a normal distribution. About, we say, approximately normal. And what value appears to be an outlier? What's an outlier? That's an exception. So normally that's either too high or too low. Compared to the values that we're looking at, well, 150 is an exception. That's way too high compared to the rest. Stem and leaf is another way of introducing data. That's something that helps you a lot with sorting different types of data. A stem plot or stem and leaf plot represent the quantity data by separating them into two parts. These are in the tens, so they put the tens right there, and the decimals right there. Right? The stem, such as the leftmost digit, and the right is another digit. And that's really how you break data and use it to separate values and look at distributions. The given data represents hourly wages in hours of 30 randomly selected college students. Construct a stem and leaf plot with the given data. 11.5, 13.4, 12.8. You know what? I know that's gonna be probably. I'll rearrange this again. 15.5, 10.9, 15.0, 12.5, 17.2, 11.2, 12.7, 14.3, 12.5, 18, 11.8, 10.9 again, 11.6, 13.5, 12.5, 16.5, 18.5, 12.4, 12.9, 10.8, 14.8, 12.9, 12.3, 15.5, 17.6, and 15.0. Now if I count those, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 30. The worst thing you could do is take data out. So 899. Zero two five six eight, 3, 4, and 3 5s, 7, 8, 9, 9. A 45, a 3 and an 8, 0, 5, 5, 0, 5, 26 and 0, 5. There. That's a stem leaf plot. What is the shape of the distribution? This is how it starts. Try to put a curve around it. This looks up. You could say approximately normal, but not really. It's skewed to the right. So approximately skewed. That's skewed really. So that's one main benefit out of looking at those types of plots. Same thing here, you know, the way we showed. Now if I look at the second page of this section, a Pareto chart is a bar graph with the condition of arranging the bars in descending order of frequency. Okay. A pie chart or a pie graph depicts categories. So this is talking about this. And pie chart is right there. This is where each slice represents a proportion of the frequency. Deceptive graphs, non-horizontal verticals. So always examine a graph to see whether the axis begins at some sort of other than 0. That's very important, which really throws off the differences. So if you look at this, you could look at that and see the difference between those and think, wow, that's a big difference. Except you'll notice they're starting at 1.75 and 2.1, 5.21, which is not that much of a difference. 5.175 and 5.21. Those are very close. If they were to start at 0, you would have noticed that those two are almost equal. And if you look at this chart, you notice they start with 50,000. They don't start with 0 and go up to 170,000. So they're starting with 50,000 to show like only the top part that is different. If they were to go down from 0 and that would look still different, but not as much as it does right now. Now it looks like there's a massive difference between those two. In reality, it's not that big of a difference. Pictographs. The given graphs are misleading because objects of area and volume are used to depict amounts that are actually one dimension. Well, think about it. This is about 18. This is 36. So this is double. But somebody looking at this looks like 5 times as big. And if you look at those, trash in 1980, 100. In 1960, 100. In 1980, this is about 160. And in 2000, this is about 260. So if this is 100, when you look at the size, this is not 2.6 times that. This looks a lot bigger, much larger. And this here looks a lot bigger than that. Even though this is 150, this is about 175. This looks way more than double that. So the graphs, you gotta look and read between the line and figure out where is the trick.